All right. Go team. Okay, so what we're going to be talking about today is light and electromagnetic radiation. And so quantum mechanics is really talking about how does light interact with matter. I mean, that's essentially what spectroscopy is. How do we talk to molecules? So let's take a look at light a little closer. So if we look at electromagnetic radiation, what that means is that there is a self-propagating wave of an electric field and a magnetic field that doesn't need a medium to go through. Much like water, where you need to actually have water waves, or actually water for the waves to go through, that's the medium. Or sound has air molecules that it's propagating through. Light is a self-propagating wave. So as you have an electric field that's moving, it creates a magnetic field that's moving. And an oscillating magnetic field creates an oscillating electric field. Magnetic field, electric field, magnetic field, electric field. And therefore you have electromagnetic radiation. Okay, just some quick vocab when it comes to electromagnetic radiation, or light waves in general. So you have a wave from crest to crest, or from one point of the wave to the next point of the wave. You have your wavelength, and that's lambda. And then if you have some sort of clock and you have a timer, and if the wave is traveling this way, you count the number of wavelengths that go through this point per second, and you have frequency. And this is per second, or given the name Hertz. Now we're going to use Hertz a lot throughout this course. This is a fundamental part of Planck's constant, which is 6.626 times 10 to the minus 34 joule seconds. So Planck's constant H has units of joules seconds. This is actually the same thing as joules per Hertz. So there's Hertz right there. So the relationship between frequency and wavelength, So frequency is equal to C over lambda. Now with my 115 students, I had a lot of fun saying, hey everyone, what's new? C over lambda. It's laugh, please, just humor me. Anyway, so the frequency is related to the speed of light. So this is 3 times 10 to the 8th meters per second divided by the wavelength. Meters divided by meters gives you 1 over seconds, which gives you your frequency. Okay. So the speed of the wave is equal to, so the speed of the wave is equal to the frequency times the wavelength. So there's the meters, there's the per second, meters per second. Okay, so electromagnetic radiation, waves in a nutshell. But one of the things I want to talk about is the electromagnetic spectrum. And so electromagnetic spectrum is an incredibly important thing for chemists. The reason being is because depending on which range of the spectrum you're in dictates how you can talk to molecules. And that's really what we care about. I mean, we care about all this physics too, but we really care about how can we talk to molecules. So if we look at the EM spectrum, we've got large wavelength, small wavelength. And if we have large wavelength, we have small energy. And actually I should add on, so E is equal to hc over lambda. Or there's nowhere to write this. So E is equal to h nu, which is equal to hc over lambda. So here's the energy. So when you have large wavelength, you have small frequency or small energy. When you have small wavelength, you have very large frequency or large energy. Inverse proportionality. Small wavelength, high frequency. Long wavelength, low frequency. Think about that for a little bit. Like, make sure that that's in your brain. Okay, so the electromagnetic spectrum. Here we go. When we have really high wavelength, low frequency, we're in the radio. Okay, and then we go from radio. Next, we get a slightly smaller wavelength. We have microwave. Then we move into the IR. Here we've got the visible. Any guesses? The UV. After that, we get the X-ray, and then we get gamma rays. Okay, so here's our electromagnetic spectrum. Really low energy. High energy, gamma rays will kill you. This is skull and crossbones. There we go. Okay, so gamma rays, really, really high energy. Low energy radio. In between, this is where chemists can talk to molecules in different ways. As you start to so first of all, let's think about radio. So radio can be anywhere from about, I want to say it's about a meter to, or a couple feet to much, much bigger. Well, think about your radio antennas. Think about how large those are. The reason they're that large is because that's the fluctuation of the, basically the pulses. And then if you look at your car, which is kind of fun, cars used to have the antennas which were about yay long. They're yay long, or about, foot or 2.5 feet or so, because that's the wavelength size of the radio frequency. You get smaller, so now we're going from large wavelength to small wavelength. As you start to get smaller, now you're into the microwave. And so microwave is anywhere from, I don't think I've got it, well, gigahertz. If you've seen on your cell phones, or you've heard of the 3G on your cell phones, microwaves in the gigahertz. This is the frequency at which your cell phones are working. You get smaller still, somewhere in this region, and you're actually going to be around the size of the water dipole. So this is your microwave. It's plugged into the wall. Okay, and this is where you put your coffee. Okay, so if you look on the front door of your microwave, you will find little bitty holes so you can see your food. Well, the reason that is because the length of the dipole for water, actually I guess I should make it that way. So microwaves are tuned to the rotation of water. And so as those microwave, the electromagnetic radiation, which is a wavelength that's associated with the microwave, it's about 2.5 centimeters, I think. 2.5 millimeters. It's tuned to the rotational properties of a water molecule. And the cool thing is, if you look at the front door, you can see those little holes. Those are slightly smaller than the wavelengths tuned to water. So when you put something in the microwave, what it's going to do is it's going to make the water rotate faster and faster. That's going to cause some friction, and that's going to heat your stuff up. The kicker is that it's in a Faraday cage, which what that means is that the electromagnetic radiation, i.e. the microwaves on the inside, are too large to go through. They won't diffract through the teeny tiny little holes, so they're slightly bigger than the holes on your microwave door. Go look at 2 or 3 microwaves. Actually don't, because you're all probably supposed to stay at home. Anyway, but yeah, go look at the microwaves and see that those things are systematically that size for a reason. Cool, we go smaller still. Now we get into IR. So now we are in bond distances. Think about why you use the IR in organic, or why you use the IR in spectroscopy. That's for you to think. What are you measuring? You're measuring molecular vibration. That molecular vibration has an energy associated with this wavelength, which is on the scale, that the quantized scale of the IR is going to be about the bond distances. You go farther still, you're going to now smaller wavelength, higher energy. You're in the visible. This is where electrons are going to start to jump up and down. Then you go even higher still, UV. Now the wavelength is so small, you're able to interact with electrons, no longer molecule to molecule or bond atom to atom or nucleus to nucleus within a bond. Now you're in the subatomic part, to where you're looking at the electron jumping up to various energy states. Go farther still, X-ray. So now you're in a much smaller energy range, much larger energy range, much smaller wavelength. X-rays are going to be so high in energy, what they're going to do is they're going to, let me see if I can find a spot. All right, so assume that this is a 2p. Here's some diagrams for you. Okay, so you have electrons in the 2p. Well, way at the bottom, you're going to have the core shell electrons, so the 1s or the 2s. Those are much more stable, which means you need much higher energy in order to interact with those electrons. In order to get there, you're going to use X-rays. And so this is how you can use X-rays to identify different atoms or elements that are much higher in the number of protons that they have. Because the higher number of protons, the higher number of electrons they have, which means they have higher energy core shell electrons. So, and then gamma rays, high energy, way high energy. Thankfully, our ozone layer protects us from gamma rays for now. Anyway, big step back. Electromagnetic radiation. A propagating electric field, magnetic field, has an energy associated with it equals to Planck's constant times c divided by wavelength, or in the Planck condition, E equals h nu. So this is the energy associated with the wavelength, or energy associated with the wave. We use these energies, and we can determine what the energies are of each of these portions of the electromagnetic spectrum. And depending on how you want to talk to your molecules, you can either talk to the core shell electrons, high energy. You can talk to the valence shell electrons, medium energy. You can talk to the infrared or the molecular vibrations, much lower energy. Then you can talk to the dielectric relaxation, which is the dipole spinning around. In the microwave is rotational spectroscopy. Or you can go as far as to the radio, which is actually how we communicate with the nuclei in the NMR. So why does all of this matter? We will be taking an approach to quantify how do you talk to light, or how do you quantify light, and how does it talk to matter? And when it talks to matter, it's going to depend on which wavelength you're in as to what you're actually asking it. And yeah, that's all. Electromagnetic spectrum.